Hi! In this series, we'll be talking about game theory and its applications. So, let's begin by in this video with an introduction into game theory. So, you might be thinking game theory is like, wow, there's game in the name, and so it is like your everyday games like that you play, like basketball, soccer, football, chess, and so on. It's not really about this type of games, but the idea behind it is that we use strategy in playing these games. In basketball, you have a plan. In football, you have a strategy. Chess, you have a strategy. And we see how our opponent reacts to such things, and we choose the best possible strategy for our outcome that gives us the best benefit. And these ideas can then be used in economic, political, and other phenomenons. So, a game situation, the final outcome is not only influenced by your own decision but also how your opponent reacts. And this leads to an interdependency, which is the very, very key aspect of a game situation. And in this interdependency, we need to choose the right strategy, and the focus will then be on strategic thinking. Like a science, game theory will be using a lot of models to model the applications that we want and see how it relates and whether it can describe a game well. It is not used to tell how we react, but how a rational person will react. And so, while it does not guarantee winning, it will help us understand the strategic interaction. So, let's start now with some basic notions. So, a game is just a situation where there are players making strategic decisions that take into the accounts the other players' action and response. The players are just always known to be rational and payoff maximizing, meaning they want to benefit themselves the most. And a payoff is just your value that you associate with a possible outcome, and we'll talk more about that later. The strategy is just a plan of action for playing the game. Action is like what you're going to do. A strategy could be because your game has multiple actions. So firstly, we need to understand what is this payoff maximizing, and basically it is because of the theory of rational choice that we say that a player always chooses an outcome that maximizes his or her payoff. And action is basically what possible moves is available for the decision maker. And in this, all the possible actions that you can choose, you must choose only a single action at that time. So then for preferences, right? What is a preference? A preference means you choose one action over the other. And the only reason to do so is by the theory of rational choice, your payoff for this action is greater than your previous. And so we can represent the payoff function as just numbers where it takes an action and gives us a number, and whatever number is greater will be the preferred choice. What we realize is that the payoff function is an ordinal, not a cardinal type of function. So if you have another type of payoff function, but these following properties holds true, that VA is always larger than VB if and only if your original function says so, then they are the same preference. And they can represent the same payoff preference. So they might be different payoff function, but they represent the same preference. So you really care more about the how one action differ. Is it a more preferred choice than the other or not? That's the most important property of the payoff function. So you can just take a look at this example. Let's just say you're going to either Havana, Paris, or Venice. So the payoff you get from choosing Havana is 1, but for Paris and Venice is 0. It is the same as saying Havana is 10 and Paris and Venice is 1, because Paris and Venice must be the same and Havana just needs to be greater. So you see, there's no really a unique payoff function to represent your preference. And again, like I said, the theory of rational choice says that we make a decision at least as good as the best available preference. So you just have a lot of actions. You just need to take the highest payoff, or maybe there's 2 actions that give you the highest payoff. Then you can choose either one of these 2, but you'll never choose something less than it. And then we can now finally, with these notions, define what a game is formally. And first, you have a set of players. So you have a tuple, and you have a set of players, and then you have a strategy space. And note that this strategy space is not an action space and are only equal when it is a simultaneous game. So what does it mean? So later we'll see that, let's say you have one move, then a second move, and third move. Then your strategy space is your action 1, 2, and 3. But an express space is just like a set that has A1, A2, and A3. It's not really a sequential thing. But if it's simultaneous, then you must choose only one at one point of time. Then it doesn't really matter. So the strategy space and action space is going to be equivalent in simultaneous case. But again, we'll take care of this in another video where we really dive into what is a simultaneous action game. And your payoff function is basically you take into account everyone's strategy and see what is your payoff, your number in the end. So this payoff function must take into account all the players' action, because there is interdependence within the players. That's how we take care of this dependence. We'll end off this video by now talking about one of the most well-known game theory examples, and it is known as the prisoner's dilemma. So let's begin with what the prisoner dilemma is, and it's basically when 2 people are caught for a crime, but there's not enough evidence to convict both of them to the actual major crime, and only for a minor offense. So what happens is that the police gives them a choice that if both of them stay quiet, they will be both convicted to 1 year in prison. But if one of them flings, which means sabotage the other, then she will be freed and used as witness against the other, who will now spend a longer time in prison. If both of them were to sabotage each other, then both of them will spend 3 years in prison. And we can represent this payoff function with the following for player 1. So suspect 1 has his best outcome, of course, is to sabotage and the other player keep quiet, right? Then he will be set free. Then the next one will be both are quiet. Then next one is both confess, and the last one will be he keeps quiet while suspect 2 sabotages him. And so with that payoff function, we can now rewrite the payoff function into numbers. So you can put this as 3, 2, 1, 0 and represent it with a bimatrix. So this allows us to write 2 payoff functions and outcomes in a very simplistic representational way. So with this bimatrix, we just write quiet, quiet, fling, fling. And quiet, quiet is a 2, so it's just 2 and 2. If you're quiet and you're fling, 0, 3. Sabotage and keep quiet, you are 3 and you're 0. And you're fling both of them sabotage each other, then it's 1-1. So with this payoff function in this view, we see that, okay, we don't know yet what is the best scenario, but it looks like, okay, 1-1 is smaller than 2-2, so it looks better to keep quiet. But when you both are keep quiet, if you think the other guy is going to keep quiet, you have a greater incentive to sabotage him. So then you try to convert to this, and likewise for suspect 2, you go over here. And in that case, isn't it likely that in the end of day outcome will be both of them confess in the end? And so both of them confess, and they are both just sentenced to 3 years in prison, which is like that's honestly what the best scenario is for the police, where both of them are sentenced to a longer prisons than what they were initially thought of. So this prisoner dilemma showcases when you should cooperate and whether you should be not cooperative. And really, this will be known as a Nash equilibrium, which we'll go through in subsequent videos. So stay tuned for those, and I'll catch you in the next one. Bye!